Just to reiterate, all talks will be invited talks are 30 minutes, 25 plus 5. The chair can give a warning at 20 minutes. And for oral presentation, it's 13 plus 2. So at 10 minutes, you can give a warning. I would also like to say that at the end of today's session, we will have the closing session where we will have feedback, brainstorming, ideas for the future, and of course, announcement for the next QMAT. So I request everyone to join the closing session, which will be around 4:15, I think. All right. So over to you, Chiranjeev.
Yeah. Okay. Thanks, Pratap. So yeah, we are starting, and today the first speaker is Professor Abhay Pashupati from Columbia University, and he's going to talk on quantum criticality in twisted transition metal Dichalcogenides. So I will, Professor Pashupati, I'll just give you a sort of raise my hand or warn you after 20 minutes. Okay, that 5 minutes are left. Okay, over to you.
Good. Okay, thank you. Okay, very good. So can you hear me?
Yes. Yeah.
Perfect.
Okay, very good. So yeah, thanks for having me, everybody, and spending your, I guess it's Saturday there morning with me. So what I want to, sorry.
No, that was some.
Yeah, can everybody please mute your microphone to avoid any background noise?
No.
Okay.
The full screen is not visible because it is hiding this, the screen, the panel at the side.
Well, I don't know. In my case, it is fully visible.
You can reduce the panel. There is a minus button you can press.
Yeah, in the top there is options, view options. So there zoom ratio you can tune.
Okay.
Okay,
So,
I think let's go ahead.
okay, very good. Very good. So thanks again for having me here virtually. And what I want to tell you about today is described in these two papers, one from last year and one from this year. So let me first acknowledge the people who have actually done this work. So my graduate student, Augusto, then a graduate student of Corey Dean's, Enmin, who is now a postdoc at NIST. And then we had a joint postdoc who is now a professor in Nanjing, Lei Wang. And one of Jim Hohn's postdocs, who is now a professor in Wisconsin, Dan Rhodes, was essential in growing some of the samples for this. And we worked quite a bit with several theorists. So a group of Angel Rubio, who's in Hamburg, and especially two of his people who have now also moved on, and then my long-term collaborator, Andy Millis at Columbia. And of course, boron nitride people who many of you, I'm sure, also benefit from. Okay, so this is a story about Coulomb interactions in narrowband systems. So all of us like narrowband systems where the width of the band is small relative to the potential energy to put two electrons on a given site. And one way of doing this that has become especially popular in the last few years with regards to 2D materials is by using superlattice potentials. So basic idea is very simple. You take, let's say, a two-dimensional semiconductor, which in 2 dimensions has a constant density of states. And if you apply a superlattice with some periodicity, then you will break up in this case, the conduction band of the semiconductor into a bunch of subbands. And within each of these subbands, the width of that band can be relatively narrow, which is set by the size of the superlattice potential in real space. And then the interesting physics that you are interested in happens in the lowest of these subbands. When you fill in electrons or holes, if it's the valence band, then you can have a relatively narrow band system where interesting physics can happen. So one popular way of doing this these days is by using so-called Moire patterning. So you take two layers and you twist them relative to each other in order to generate this kind of superlattice potential. And the real technical advance in this field was most recently from Emmanuel Tutuk's group in Austin, who invented this very beautiful way of taking one sheet and then tearing it into two and twisting it. And of course, previous to that, my colleague Corey Dean and other people at Columbia invented this method for stacking materials on top of each other, which is also one of the basic requirements for this. Okay, so in this field, one of the findings that has now been seen for a whole bunch of different types of materials is the fact that when I look at this lowest conduction band or lowest valence band, and I start to fill electrons or holes into it, then when I have exactly one or an even number of, any integer number of electrons per unit cell, and unit cell here means the Moire unit cell, then the system shows insulating behavior, very reminiscent of Mott insulators in strongly correlated materials. And this kind of behavior has now been seen in lots of different systems, so twisted bilayer graphene, double bilayer graphene, and so on and so forth. And there's sort of too many references now to list here, so I just put down some of these systems. And so one part of this talk, or the first part, is similar finding of this kind of insulating behavior driven by correlations in one family of this. And the particular material that we are interested in is tungsten diselenide. Now, this material is a pretty boring semiconductor in monolayer form. It's a close cousin of graphene. It consists of tungsten and 2 selenium atoms per unit cell. And look from the top, it kind of looks like graphene. And if you ask what the electronic structure of this material is, it looks like graphene with a large band gap. So it has conduction bands and valence bands, and there are 2 valleys, one at the K point, one at the minus K point. And all of the physics that we are interested in is happening in the valence band of these materials. And at low energy, you can essentially think about this as having 2 valence bands, one at K and K prime. And the meaning of these colors is to tell you about the spin direction in each of these valleys. Due to strong spin orbit coupling, you have only one spin projection in each of these valleys. So you can think of the blue color as spin up electrons and red color as spin down electrons, if you wish. So in terms of band structure, this is actually simpler even than twisted bilayer graphene, which has both spin up and spin down electrons in each of the valleys. Here you have only one spin projection per valley. And so if you look within the lowest valence band, subband, which is what we're going to talk about, the physics essentially means that you can have 2 holes per Moire lattice site. So it's a very simple triangular lattice with 2 carriers per site. And when you take 2 of these layers and you twist them relative to each other, then here is a picture of what the band structure should look like according to theory. This is DFT theory. And this looks at first sight somewhat complicated, but it's actually not that bad. So if I look at this solid line here, this is the original valence band from one of the layers. If I look at this dashed line here, this is the valence band from the second layer. And when 2 layers are touching each other, there's some hybridization gap that opens between the 2 layers. So then that's the total band structure. And once again, all the physics that we are interested in happens when you're filling holes just in this topmost of the bands. And you shouldn't worry too much about all of these other bands. Okay, so here's how the samples actually look like, at least schematically. You have this bilayer of tungsten diselenide, and it has dielectrics on the top and bottom, hexagonal boron nitride. And then there's gate electrodes on the top and bottom. If you apply the same voltage to both of these electrodes relative to the tungsten diselenide, you can add charge to the tungsten diselenide capacitively. And if you apply equal and opposite voltages to the top and bottom, then you end up creating a pure electric field across this bilayer. So here are some transport data on one of these samples. So what's shown here is the resistance as a function of filling. So here is the edge of the valence band, and then going in this direction is you're filling in holes into the valence band. And I'm showing you this blue curve. This blue curve is taken for a sample which has a twist angle of 4.2 degrees. So it has a superlattice. And then this black curve is for a sample that has twist angle of 60 degrees, which is the natural form in which this material occurs, the Bernal stacking. And you see that this black curve has a difference from this blue curve in that at a particular value of the density, this blue curve shows a peak. And this peak corresponds to an insulating state. So if I measure this at lower temperature, this peak will start to get higher. And so this is the signature of this insulating phase at exactly 1 electron per unit cell, or 1 hole per unit cell. And here is temperature dependence, showing that indeed, as you sit at this particular point, the resistance, which is initially metallic at high temperature, it turns over and then becomes insulating at low temperature and keeps going up. And if I'm not precisely, I'm sorry, I'm not sure why my computer is behaving so strangely. If you're not sitting exactly at this half filling point, but I'm sitting somewhere here away from this half filling point, if you measure the temperature dependence is essentially monotonic and occasionally goes to 0, although we are yet to confirm that it's superconducting. We can also measure magnetotransport, so we can put this in a large magnetic field. If you do that, you see nice Landau level quantization at high field. And this is very useful to tell us exactly what the filling is. So we know that this point is precisely half filling of the Moire unit cell. And also the Hall effect tells us about the sign of the carriers. Okay. Now we've done this for a range of samples which have a range of twist angles. So shown here are a few different twist angles. And if you go to different twist angles, we always see this insulating peak, but the position of this peak with density changes. And that is natural because as you change the twist angle, you're changing the size of the unit cell in real space. And so you're changing the filling required in order to fill 1 hole per unit cell. But this peak always happens exactly at 1 hole per unit cell. Okay, so all that I've told you about so far was about what happens as a function of density. You can also ask what happens as a function of this other tuning knob that we have, which is the electric field that you can apply to the system. And if you apply electric field and density, and I can explain later if you're interested why this plot looks as funny as it does. The essential point is that there is a region of electric field and close to this half filling point where the system is an insulator. And if the electric field is too small or the electric field is too large, then the system is a metal. But for this intermediate range of electric fields, the system is an insulator. And that's schematically shown in this red elliptical region. And this is data for 2 different samples. Now you can ask, why does it show this kind of behavior? And we can gain some insight into this from what the electronic structure does as a function of this electric field that you apply. Now, remember that if I have a bilayer system and I apply an electric field perpendicular to the layers, then I have a difference in the potential energy for electrons in one layer versus the other layer, just integral of E dot dl. And so when you start to apply this electric field, the valence bands on each of these layers, which were originally degenerate, are now going to be displaced relative to each other. And so this you can see here, this is once again the DFT calculation done at 0 electric field and done at some non-zero electric field. As you start to apply this electric field, you see that these 2 originally degenerate valence bands now start to displace from each other. And so effectively, you can tune the band structure and the bandwidth by applying an electric field. So the electric field tunes the bandwidth of the system. Now, you can go even further and ask in theory, what does the band structure look like only within this topmost valence band? If you do that, here's a picture of what DFT tells you for the band structure. If you look at the density of states, at zero electric field, the density of states has a peak, a Van Hove singularity, which is around 0.4 times the filling. So it's on one side of half filling. And as you start to apply this electric field, this peak goes to half filling first. And then as you keep applying more electric field, this peak goes through half filling and goes towards full filling. So there's a range of electric field where this peak in the density of states is close to half filling. And to cut a long story short, this is more or less where we see insulating behavior appear in the sample. So then the picture that arises is that the insulating state in this material is driven both by the fact that the density of states can be high when you tune the electric field properly, as well as correlations. And we have some support for this theoretical picture from the Hall effect. You can measure directly where this Van Hove point lies by the sign change of the Hall coefficient. Okay, so now this is sort of work that we did last year. And one question I had, and you can generally ask is, so what is the big deal about this? Because after all, we know lots of Mott insulators in this world, and lots of them have temperature scales that are hundreds of Kelvin and gaps that are very large and so on. And what is special about these kinds of systems? And in my view, what's really nice about these systems is that you can tune through a phase diagram simply by applying electrostatic gates. So normally, if you're studying a traditional correlated materials family, the way you tune through this phase diagram might be you make different samples with different doping levels and look at their properties. Here, just within one sample, while keeping all the other properties fixed, you can tune through this phase diagram both in density as well as in bandwidth. And in traditional materials, pressure, for example, is one way of doing this to some extent, but here you have really lots of control in multiple axes. So again, coming back to traditional correlated materials, many of the most interesting phenomena, the phenomena that challenge us intellectually, are not found so much in the insulating state, the Mott insulator, but what happens when you start to dope this Mott insulator. When you dope this Mott insulator, the system in general becomes metallic, but it's not a great metal, it's a strongly correlated metal. And that's when you can have all kinds of interesting phases, all kinds of unexpected surprises as well. And one thing in general is that these kinds of phenomena are, while they're very interesting, they can be delicate to measure. They're not very easy. They just don't show up always very easily in a transport measurement or even a spectroscopy measurement. So we were interested in these kinds of materials to ask the question, what happens when I start to dope away from this Mott insulator, either as a function of density or as a function of electric field? Can we see evidence for anything interesting happen in the metallic phases that are close to these insulating phases? And so we've done some first work along those directions, which I want to describe to you now. So what we do then is we look around this insulating region. So this is this elliptical region. And then we go through this elliptical region. And in this case, we're just measuring transport as you go across this metal to insulator transition. And the first thing we noticed that was very interesting is that if you measure what the insulating gap does as a function of either density, which is this purple line, or electric field, which is this light blue line, you can measure a gap whenever the system is insulating simply by measuring Arrhenius gap from resistance. And if you measure this gap, you see that this gap goes continuously to zero. So at the metal to insulator transition, it looks like this gap really goes to zero continuously. And this is somewhat unusual in these kinds of systems. Quite often in, say, complex oxides, when this kind of metal to insulator transition happens, there's also strong coupling to lattice degrees of freedom. And this makes a transition first order. So here it looks like at least the system might be a second order phase transition. And in that case, one might imagine, is there any possibility that there would be a quantum critical transition at this boundary? And so in order to probe that, what we do is we look at transport carefully when we are near these metal to insulator transitions. And you have, if you tune density, you have 2 metal to insulator transitions on either side of this half filling point. And if you tune electric field at half filling, once again, you have 2 metal to insulator transitions. So let me first show you some data that is taken along the density axis. So here is the half filling point. Sorry, it's written as -1 in this notation, but that's the half filling point. And as I tune the density, I have 2 metal to insulator transitions that happen here. And this is showing you what the temperature dependence of the longitudinal resistance does. And if I take a temperature derivative of this longitudinal resistance, then I can clearly see the regions of insulating behavior. These are regions where d rho dt is negative, and that's bounded by this dashed white line here in a dome form. And at this boundary is now the metal to insulator transition. And if you stare at this d rho dt plot, you realize that close to this metal to insulator transition, this color scale is relatively uniform. And if d rho dt is a constant, this tells you that rho is linearly proportional to t close to this metal to insulator transition boundary. And if you dope a little bit further away from this metal to insulator transition boundary, then it becomes non-linear. And I'll show you a little more data on this. And the same thing happens for the other metal to insulator transition boundary as well. Okay, so let me now show you a little more data over an extended range of temperature. This is now up to 200 Kelvin, and also an extended range of doping. So let me show you some line traces to show you what the evolution of the temperature dependence looks like. If I sit very, very far from this insulating phase, and I measure the temperature dependence or resistivity, and I look at low temperature, then you can perhaps see this little curving of the resistivity at low temperature, and it's reasonably well fit by a t-squared form with some coefficient at low temperature. As I start to approach this insulating phase, you can see much more clearly, you can see a beautiful t-squared form at low temperature. So this is somewhere close to, but not very close to the metal to insulator transition. And if I come exactly to the metal to insulator transition point, so at the interface, you can see that it's now T-linear, and this linear transition temperature goes all the way down to the lowest temperature of our measurement, which now is around 50 millikelvin or so.
Professor Pashupati, 5 minutes left.
Okay, thank you. So let me keep going along this direction. And here now I'm going to the insulating phase. And if you look at the actual insulator itself, then at low temperature, the resistance starts to go up, but just above the metal to insulator transition, once again, there's a little region of T-linear behavior after which the resistance rolls off. If I go over to the other quantum critical point, or let me call it quantum critical point, once again, I see T-linear behavior down to low temperature. And if I go even further, then once again, it starts to curve and I start to see T-squared behavior reappear in the system. So I can summarize all of this data in this color-coded plot, which tells you in which range of temperature, what power law fits the resistance well. And what emerges is that there are 2 what look like quantum critical fans of T-linear behavior, which project to the metal to insulator transitions on either side of the insulator. And so this very much looks like quantum critical points on either side of the insulator. Now, one of the classic signatures of quantum criticality in, say, the heavy fermion systems is obtained by looking at these coefficients of the temperature dependence of resistivity. So let's look at the temperature dependence of the T-squared coefficient and at the T-linear coefficient at different points in this phase diagram. So if I do that, then if I'm very far from this half-filling point, so the half-filling point is far from here, then I see that this temperature coefficient of T-squared behavior, so here this is the temperature dependence of T-squared behavior, is more or less a constant. But as I approach this quantum critical point, this coefficient really diverges by about 2 orders of magnitude. And at the quantum critical point, this becomes large, bounded by disorder. And similarly, if I approach the quantum critical point from the other side, again, I see this strong enhancement of this T-squared coefficient, which corresponds to a collapse of the Fermi energy as you reach the bottom of the band. And corresponding to that, if I look at the coefficient of the T linear behavior, the coefficient of the T linear behavior is maximized at the quantum critical point. And just in terms of numbers, this, interestingly enough, this number is comparable to the so-called Planckian bound, where the scattering rate is given in terms of temperature. Okay, so finally, before I conclude, in many correlated materials, also anomalous magnetoresistance has been observed at low field. And in our materials as well, we see this anomalous magnetoresistance behavior. So if I measure the resistance as a function of magnetic field, so here are shown a set of traces. This red curve here is taken far from the quantum critical point, and the top blue curve is approaching the quantum critical point. If you're far from the quantum critical point, perhaps not very obvious here, but you can take my word for it that the B dependence is B squared, as one expects for a simple metal. But as I approach the quantum critical point, first is you can see that the response, this is not scaled in any way. This is the real response as a function of magnetic field, becomes very strong. And second is you see this very clear region of linear in B behavior that's observed. Again, this has been observed in other materials like cuprates and Nickelates. And there's an ansatz that I think James Analytis and others have used to describe this kind of crossover behavior from B squared to B. So if this gamma number is large, then it's like a B squared. And if gamma is 0, then it's B linear. And you can see how this crossover from B squared to B happens as you approach this quantum critical point. Finally, one last thing is everything that I told you about so far is as a function of density, but you can do the same experiment as a function of electric field. And if you do the same experiment as a function of electric field, the result is fairly similar. You can see that there's a region where the sample shows insulating behavior at low temperature, and then there's a region where the sample is metallic. And if I look at the interface between the insulator and the metal, you indeed see T-linear behavior. At the time we took the data, we were not looking for this effect, which is why we did not take as many data points as we should have. We are now repeating these experiments, taking better data. But you can reasonably well see that there's a T-linear behavior at that quantum critical point driven by electric field. And if I go further into the metallic phase, I see once again metallic behavior with T-squared dependence. So let me skip over this and let me then just conclude and say that this system looks like a Mott insulator, but with a continuous metal to insulator transition in the system. And it looks like around this ring of metal to insulator transitions, there are quantum critical points. Now, one of the things we really need to identify is what's the nature of these insulating phases. We have some evidence that this looks like Néel order, but yet to be conclusively shown. Also, what is the nature of the metallic states that are close to these insulating states? One of the exciting possibilities is on the boundary of the metal to insulator transition. On the insulating side, you might have spin liquid states, for example. Is there a way to measure it in this system? These are all questions that we hope to answer in the future. So let me stop here and thank you.
Well, thank you, Professor Pashupati. So this thing is open for discussions and comments. Pratap, so there is a queue. Pratap, please.
Hi, Abhay. This was a spectacularly interesting work. So one question that I have here is, in many of the systems, electronic systems where one has a quantum critical point, the true quantum critical point is sort of thwarted by an order. Here, is there any evidence of any order emerging close to the quantum critical point?
So not so far, but I should say, we are still somewhat early in measurements, right? So one thing that is already, we know that there has to be a little bit more to the story. For example, we see that as a function of density, that the insulator survives to about 10% doping away from the half filling point. And theoretically, that would be, not reasonable, right? So whether there's something else going on, there are other states on this boundary is yet to be determined. Let me say. So, the problem is that there are not that many measurements one can do on these systems.
Yeah.
So
Okay.
That's yet to be determined.
Okay.
Okay.
Thank you.
Tanushree.
Yeah, thank you for a very nice and wonderful talk. I just wanted
Thank
to
you.
know, effect of spin-orbit coupling, is anything known?
Yeah, so in these systems, the spin-orbit coupling basically freezes the spin out of plane. So one of the consequences of this, for example, is if you apply in-plane magnetic field, which you might like to do to introduce some Zeeman effect into the system, in these systems, it's more or less useless because you can think of the spin-orbit field as basically having a zero G factor for fields in the plane. So yeah, it's fairly simple, it just makes the spin stay out of plane.
Okay. The other question is there...
Just once, because we are running out of time, maybe we can have discussion later. So maybe Sumilan, I will give just one last question and then we'll go to the next topic.
Okay, thank you, Chiranjeev. So, Abhay, one question I had is this: apart from lattice effect, so there are also effects of disorder, and also, so these long-range interactions come into play, like in the Mott transitions, right? Like excitons and all. So, why those are not important here? Is there any understanding?
Oh, I didn't say that. So definitely there is disorder in these systems. I haven't talked about it. We've done some STM measurements and we have now a little bit of quantification of disorder in this system. So definitely disorder is there. I think all I can say is that as a function of the tuning parameters, the disorder is not changing. But disorder is definitely there. And in this field, everybody has more or less just ignored disorder so far. But we'll discuss that in the next works, hopefully.
Okay.
Actually, sorry, Rajdeep and Bhima, we are out of time. We can discuss with the speaker in the breakout box if he's available.
Go ahead.
So yeah, so we will go to the next talk. So Tanushree, can you put your slide? So next we have Professor Tanushree Dasgupta from SNBOSE Center for Basic Sciences. And she's going to talk on orbital selective superconductivity in infinite layer Nickelates, role of non-zero f-ness. I will give you a warning after 20 minutes. Okay, please.
Thank you. This talk starts with a disclaimer that I have changed the title, but not the content of the talk. So I have just changed the title to make it more appropriate with the content. So the title of my talk is Axial Orbital Driven Superconductivity, A Tale of Two Ages. And the collaborators in the talk, the primary content of the talk is by Shubhadeep Bandyopadhyay, who was a former PhD student of Indra Dasgupta from Cultivation of Sciences. Priya Adhikari, the PhD student of Dr. Tanmay Das from IISER Bangalore, and the talk is based on the two papers we had in last year. So as we all know, since the discovery of superconductivity, the goal has been how to enhance the superconducting transition temperature, and that basically shows a kind of a timeline. We have definitely the very famous cuprate family. And following that, we have the age of the Rn compounds. And in very recent time, the superconductivity Nickelates have been discovered, entering the nickel age of superconductivity. So let me start with the cuprates, although I would like to get into the Nickelates, but there is a connection between the two. So I would like to start from the story of the cuprates, which is basically the story of the axial orbital. And this is some work we did quite some time back, but in recent time, also last year, we had a work which is connected to what we did in the past. So this is the phase diagram of the cuprate, which is very well known in this audience. So all the copper oxide family, they basically shared the same kind of phase diagram with a dome-shaped superconductivity with the maximum point of this dome, which is the TC at optimal doping. that shows a very large material dependence. For example, in case of the lanthanum cuprate, this Tc is 40 Kelvin. While you go to the mercury compound, this is more than double, this is already 90 Kelvin. So even today, there is no clear consensus in the theory of ITC superconductivity of the cuprates, except that the strong correlation plays an important role, but what exactly is the role of phonons and etc. is still very debated. But admitting that, where does this material dependence come from? And if you really look at the Fermi surface of these two compounds that I mentioned, the lanthanum cuprate and the mercury cuprate, the Fermi surface of the mercury compound is much more rounded, while in case of the lanthanum compound, it's much more squarish. That's just from the photoemission data that shows in the overdoped regime of this cuprate. And this is the Fermi surface calculated from the density functional theory, and one can define a delta K. And this delta K can be actually defined with the parameter R, which is quite different between the lanthanum compound and the mercury compound. And we did basically a same exercise for the all known whole-doped cuprate long back in 2001. And if you just follow the black symbols for the sake of time, I'm not going to explain in detail this curve. So here in the y-axis, this is a semi-empirical curve in the sense that in the y-axis, it is the optimal Tc at the optimal doping, which is measured, while this R parameter is basically calculated from the Fermi surface plot. And you can see a really nice correlation between this R parameter and the Tc at optimal doping. Now, the question we asked, which structural elements determine this R? And this is the DFT band structure of this compound. Any typical high Tc cuprate, there is a single band that is crossing the Fermi level, which is the zero of the energy. If you really look at the wave function, corresponding to this single band, which is basically projected in two planes, namely the copper oxygen plane and out of the plane projection. What you see, and that is plotted for the two compounds, namely the lanthanum compound and the mercury compound. For the lanthanum compound, it is much more localized in plane, while for mercury compound, it's much more delocalized in plane. On the other hand, for lanthanum compound, there is a quite appreciable out of plane extent, but for the mercury compound, it is completely confined to the plane. So already this wave function actually looks quite a big distinction between the lanthanum and the mercury compound. And from the out of plane composition of this wave function, what you can actually conclude this out of plane extension of this effective wave function that basically describes this single band crossing the Fermi level. This is arises because of the hybridization between copper 4s, which is actually empty, and that interacts with the apical oxygen, because all these structures has an oxygen atom sitting out of plane, as I will show a few slides later, and coupling with the copper 3z squared. And that basically gives rise to an effective orbital that we call as an axial orbital, formed as a result of hybridization between copper S, apical oxygen PZ, and copper 3z square, and maybe even some outer plane like lanthanum degrees of freedom. So starting with such a kind of a model, which is basically a 4-band model, because you have a copper D, you have the oxygen PX and PY, and added to it, you have the axial orbital. So it is a 4-band model in contrast to the much discussed MED model, which was a 3-band model. But starting from such a 4-band model, you can actually derive a 1-band model, which describes the single band crossing the Fermi level in terms of the long-ranged 1-band model, which consists of T, T prime, T double prime. And you can define a range parameter, the same R parameter which we have seen before, in the sense this R is now a ratio of T prime by T, and all the other long range interaction like T double prime and so on and so forth, they are basically various powers of this R. And with the detailed calculation, you can actually show this range parameter R of this one band model is essentially it depends on the position of the energy of this axial orbital. Now, if you really look at the crystal structure of these two compounds, this is what I was mentioning, that you have a copper oxygen plane, but you have some out of plane oxygen, and that is what we call the apical oxygen. And the distance between the apical oxygen to copper oxygen plane is quite different in this two compound, being 2.4 angstrom for the lanthanum compound and 2.8 angstrom for the mercury compound. And plotting this range parameter R to this structural parameter, namely copper oxygen plane to the apical oxygen, you do see a kind of a dependency. So this R is therefore controlled by the distance, the structural parameter, the distance from copper to apical oxygen and the bonding of this apical oxygen to this out of plane orbitals. So therefore, for the cuprate, our understanding was the following, that the essential material dependence is contained in a single parameter R, and that is controlled by this axial orbital, which is a hybrid between the copper S, copper 3Z square, apical oxygen PZ, and further orbital. And we concluded also the materials with larger R tend to be those with the higher observed value of TC at optimal doping. Now, with this, success and excitement and also debate of the cuprates, the attention was kind of driven to the other transition metals, namely the iron, and then what about the nickel, which has been discussed for quite some time. Starting with the copper 2 plus in cuprate, if you can make nickel 1 plus, they have the same electronic configuration like D9, so that gave a lot of hope. And following this, there have been actually quite a large number of atoms by making some super lattices, as well as the solid state chemists making 2-layer and 3-layer nickelate compound with a goal to create such a kind of nickel 1 plus valence compound. Therefore, it actually created a lot of excitement when in 2019 from the Stanford group, the Harold Wong group, they basically reported superconductivity in neodymium doped, in strontium doped neodymium nickelate with the TC which is not very high, but still finding out superconductivity in this nickelate compound was a very big achievement with the TC which is within 10 Kelvin. Now, this led to many different open questions, and are cuprates and nickelates similar kind of animals, or are they different? To start with, even in the undoped situation, they are quite different in the sense that the nickelates are paramagnetic metals vis-a-vis cuprates, which are antiferromagnetic insulator. The cuprate, we all know, can be actually described with an effective single band. Is this description still works for the nickelates, or we want to go to a multi-band description? There is spectroscopic evidence of that possibly in case of the nickelates, a multi-band description will be much more suitable. So this is the density functional theory band structure of the compound. We took two compounds, namely the lanthanum nickelate and the neodymium nickelate. So on left, what is shown is the band structure of the neodymium nickelate, and in the right is that of the lanthanum nickelate. And what is interesting, you of course have this single band that is crossing the Fermi level, and which is basically nickel x square minus y square band shown with this orange fatness. But in addition, there is another band that is crossing the Fermi level and giving rise to electron pocket, and that primarily comes from neodymium or lanthanum 3z² and XY, and that gives rise to two pockets, one at the gamma point and another pocket at the A point. And if you really look at the Fermi surface, you find that the Fermi surface looks more like that of the cuprid, but with a big exception. Around the gamma point, you do have a pocket, which is this electron pocket. And the size of this electron pocket is quite different between the neodymium and the lanthanum compound. And this is also evident if you look at basically the wave function or the one-year function that describes these two bands. They are quite similar for this orange colored band, which basically shows it is x square, nickel x square minus y square, that makes anti-bond with the 4 neighboring oxygen and pretty similar looking. But the other one-year function, which we call as an axial orbital, in the same spirit as that of the cuprid, the shape of this axial orbital is actually quite different between neodymium and lanthanum. Lanthanum being much more spherical kind, while it is much more cylindrical in case of the neodymium compound. Starting with such kind of a band structure, we basically derived a low energy 2-band model of this compound, and we looked at the spin fluctuation mediated pairing within RTA kind of scheme. So we had an interaction where the interaction parameter U is basically the interaction between the same orbitals. So it has two different values, one for the D channel and another for the axial channel, while the V is the interorbital interaction. And solving that within such a kind of scheme of this wick coupling, the rationale for using the wick coupling theory was that the nail temperature is much smaller, the magnetic interaction is much smaller in case of the Nickelates compared to the cuprates, as you can estimate from their nail temperature. And it doesn't even order because the magnetic interaction is quite weak. And this basically shows the plot of the pairing eigenfunction in the two channels, one in the D channel and another in the axial orbital channel. In the D channel, we discovered the same dx² minus y square kind of pairing symmetry. But in the other channel, in the axial channel, there is an evidence of this gapless kind of a gap. And so therefore, this leads to an orbital selective pairing in case of the neodymium compound. In case of the lanthanum compound, since the electron pocket diminishes and becomes very small, what you have is only the dx² minus y square kind of pairing, the pairing in the axial channel being almost negligible. Not only that, if we really look at the pairing eigenvalue, the lambda, we find it has a very strong dependence on V, and it becomes appreciable only when the V parameter becomes appreciable. That is basically the intra-orbital interaction. And if we make the V really small, then it doesn't have much dependence on the U parameter. So the superconductivity in this compound therefore comes because of this primary key factor, which is driving this thing, is the interaction, interorbital interaction parameter V. So therefore, axial orbital has a big role, but it has a two different kind of role in cuprates and Nickelates. In cuprates, it has a passive role, indirect control of electronic properties. In case of the Nickelates, from passive, it becomes very active and it participates directly in the superconductivity. Now, the next question was, is neodymium Nickelate the only candidate for Nickelates superconductivity? Well, the answer was no, because then there was the next paper from the Harald Wang group again, where they discovered superconductivity also in the praseodymium compound. So that raised the role, what is the role of these f orbitals, because both neodymium and praseodymium are rare earth compound. Is there any role of 4f magnetism? But it was not very clear, because praseodymium is F2 occupancy, while neodymium 3 plus is F3. So therefore, there is a difference in electronic F electronic configuration of praseodymium and neodymium, but still the superconducting PC was similar between the two. And this is basically the calculated band structure, but now of the three compound, the lanthanum compound, neodymium and praseodymium, and the band structure of neodymium and praseodymium turned out to be rather similar in terms of the size of this electron pocket at the gamma point being very similar. While for the lanthanum, as mentioned already, the electron pocket diminishes at the gamma point quite a bit. And this is also seen in terms of the two band density or state of this three compound, the blue one being the density or state coming from the nickel x square minus y square, and the black one is from the axial orbital. The zero of the energy, as usual, is set at the Fermi level, and this is the weight below the Fermi level for the praseodymium and neodymium of this axial orbital is about 12%, while in case of the lanthanum, it is reduced to 7%. So then we calculated basically the superconducting order parameter as a function of doping. We could not do for to the small doping range because of the technicality of the weak coupling theory. But what we found that for the neodymium and praseodymium, the superconducting order parameter is pretty similar. The strength of the superconductivity is quite similar between the two compounds, irrespective of what is the value of V we are choosing. But in case of the lanthanum, first of all, we find that the superconductivity is present. It is not that the lanthanum becomes non-superconducting, but with the superconducting strength of the superconductivity, which is about half or less than half in case of the lanthanum compound. So to summarize on this part, on the Nickelates story, what we found that the Nickelates that forms an axial orbital resulting from hybridization of neodymium, praseodymium or lanthanum 3z square with that their xy orbital, the nickel 3z square as well as nickel s. So this is a hybrid orbital arise because of the interaction between all of these. So while in case of the cuprate, this axial orbital plays the role of mediator, it takes an active role within the two-band scenario of this Nickelate. The pairing strength depends crucially on this interorbital interaction, the V term, and there exists an orbital selective pairing state with the x square minus y square symmetry in the nickel D channel and gapless 3z square symmetry in the axial orbital channel.
Tanushree, you have 5 minutes.
Yeah, I think I'm more or less done. I'll be done in 2 minutes. While the active role of the F electrons is debated, because in our calculation, we have put really the F in the core, but what is actually talking about is the role of the F electron in influencing the position of the empty 5d levels of the rare earth, dictating the nature of the axial orbital. It is found to drive two-gap superconductivity for the praseodymium and neodymium compound as opposed to a single gap in the lanthanum compound, because as already mentioned, because of the diminishing of this electron pocket, in case of the lanthanum compound, only one channel becomes operating. And these actually leads in the doping-dependent superconductivity, a factor of 2 separation in the strength of superconductivity in lanthanum compound as compared to that of neodymium and praseodymium compound. And after our paper was published, there was this report again from Harald Wang's group. They discovered the superconductivity also in the lanthanum compound, which is actually an age-old problem. Many people have tried to discover superconductivity in lanthanum nickelate, but finally it was successful, and they could discover nickelate superconductivity without rare earth magnetism. And this is basically the kind of phase diagram that was reported in their paper. And of course, the details of this phase diagram, I mean, details of the shape of the dome and etc. is not, you cannot really have a quantitative agreement between what we propose and they are proposing. But the interesting thing is they indeed find almost a factor of 2 separation between neodymium and praseodymium TC at the optimal doping or the highest doping, because the shape of this dome is also quite tricky and funny. So it is a bit difficult to tell what is the optimal doping. But nevertheless, while it is quite similar, the highest point of this dome between praseodymium and neodymium compound, in case of the lanthanum compound, it is suppressed and it is about a factor of 2 as we have proposed. So with that, I would like to end my talk, and I will be happy to have any question that you may have.
Okay, it's open for discussion and questions. So, anyone? Yeah, Patnaik ji. Yeah.
Thank you, Professor Saha Dasgupta, for a beautiful talk. But I think from the theory point of view, is there a parallel with cuprates? I mean, like the nickel +1, as you rightly said, is I mean, there's no magnetism and there's no antiferromagnetic, there's no Mott insulator type behavior, right? So expecting this similar dome structure like cuprates, is it what you would expect from the theoretical perspective? I mean, why should there be a parallel between cuprates and nickel-based nickelates?
No, the parallelism people thought because you have both a transition metal and both have a D9 configuration. The difference between the two comes because while the cuprate are more like charge transfer insulator, in the sense that if you really look at the position of the oxygen levels, which are very close to the copper D level in case of the cuprate, that situation is quite different in case of the nickelates because the oxygen levels are far below the nickel D level. So this is more in the Mott limit rather than the charge transfer limit. But then you can actually ask that what happens to the magnetic exchanges? The magnetic exchange scale is much smaller to that of the cuprate. So therefore, it doesn't lead to any magnetic ordering that can be detected, or the transition temperature might be too small. But beyond that, there is a kind of a great similarity between the two, but with subtle differences, as I was trying to point out, because of the role of this multi-band superconductivity.
But the centrality of doping a Mott insulator, is it valid in this case?
For example, there was a calculation of electron-phonon coupling, and the electron-phonon coupling turned out to be so small, it cannot account even for some 5 to 7 Kelvin of superconductivity. So the only way, the model we had is actually with the Hubbard model with the U and V term.
Pratap?
Yeah, so this is probably not the right question to ask you, but what I wanted to know is that nickelate, why did it take so long to synthesize? Are there challenges since people have tried various oxides?
Yes, absolutely. I mean, whatever I know, I can tell you is in the sense other than the Harald Wang group, nobody else could actually report this. So there must be challenges with and for the Harald Wang, all of them are thin films. They are not bulk sample. So there can be a lot of issues with how you are really making this thin film, because not for the neodymium or praseodymium, but for the lanthanum compound, it is a very age-old problem, and people have tried in the bulk sample and they didn't actually succeed. So the trick might be making such thin films and how you are making this thin film. Yes, absolutely. But it is for you people to really answer this.
Yeah, it is quite challenging actually. Very challenging. Yeah, it's very difficult.
I see.
Okay, so let's move on to the next talk. It's already 10 o'clock. So thank you, Professor Dasgupta. So next is Goutam Sheet, and his title is very interesting, where two insulators meet. Okay, Goutam.
Am I audible?
Yeah.
Yeah, well, the title is not that interesting. I asked the organizers to change it somehow. They did not do it. That's okay. This is the title that I wanted. It's a superconductivity with a rewritable magnetic memory at LVU-STO interfaces. So the previous talk was about high temperature superconductors, and I will talk about extremely low temperature superconductors. In order to make this transition smooth, I will go through some general slides, starting with the remark made by Pauli long time ago, when he said God made the bulk and the surface was invented by the devil. Now, I think of the surfaces as the interfaces between a material and the rest of the universe. And that is most beautifully seen in the 3D topological insulators, where the vacuum can be thought of as a, let me find the laser pointer, as a trivial insulator. And we have the inverted band gap in the topological insulator. And the surface of the topological insulator is actually an interface between the two types of insulators. That's why the interface becomes hosts conducting surface states, the spatial spin momentum locked surface states. So interface is always quite interesting. And in fact, we found that the interfaces of different materials can sometimes be superconducting, where the materials themselves are not superconductors. We found that the interfaces between these 3D Dirac semimetal cadmium arsenide and the normal metals, and also the wild semimetal tantalum arsenide and normal metals like silver and so forth, become superconducting. But I'm not going to talk about that today. Today, I'm going to talk about the interfaces between insulators. The story began in 2002 when this kind of super lattices between LTO, lanthanum titanium oxide, and STO, strontium titanium oxide were made. And it was seen that the interfaces between these materials became conducting. They in fact formed two-dimensional conducting electron gases. The explanation was that it came in 2004. It said that charge transfer from LTO to STO causes the formation of such two-dimensional electron gas, which is conducting at the interfaces between two insulators. But the same group discovered another high mobility electron gas at LAO-STO interfaces, where LAO is lanthanum aluminum oxide, and this came in 2004. And in this case, what was seen is that the films were made by pulse laser deposition, and prior to pulse laser deposition, the STO substrates, the surface of that is prepared in a controlled way, in which one can get titanium oxide terminated layers on the top or strontium oxide terminated layer on the top. It was seen that when the starting material had the titanium oxide terminated surface, the two-dimensional electron gas formed, which is conducting. And when the surface was strontium oxide terminated, the interface remained insulating. And also there was a dependence on the critical thickness of the lanthanum aluminate layer that was grown on top of strontium titanate. And only when the thickness of the LAO was above 4 unit cells, the two-dimensional electron gas formed. And how many unit cells are deposited can be counted by counting the number of peaks in the read pattern, which is done in situ during the growth of the LAO layer. And these interfaces are actually quite sharp. And the idea of the formation of the two-dimensional electron gas was that there is a polar catastrophe. This is the idea of polar catastrophe. And that is when you have a non-polar substrate like strontium titanate. And on top of that, you grow a material which is polar, like lanthanum aluminate. Then the potential builds up leading to a potential catastrophe. And this can be avoided. This catastrophe is resolved if half the charge per unit cell from the surface is transferred to the interface. The catastrophe is resolved, and as a consequence, a two-dimensional electron gas is formed at the interface. Now, in 2007, such interfaces were also shown to superconduct. The first one in LAO-STO was shown to superconduct below 200 millikelvin. And following that, LTO-STO interfaces were also seen to superconduct. And most recently, there was a report of 2 Kelvin superconductivity at the interfaces between EUO and KTO, which is potassium tantalum oxide. And today I'm going to talk about a new interface which superconducts. I want to make a note here that even in case of LAO-STO, it is known that superconductivity happens closer to the STO part of the interface. So it is possible that the superconductivity is coming from the superconductivity that is already known for STO, particularly delta doped STO. But that is okay for us because the entire STO does not become superconducting. Effectively, we get a two-dimensional superconductor, which is confined only at the interface, regardless of its origin. And LVO is an interesting compound, and I will talk about that. And before that, let me talk about the interfaces that we had. This was made by Shubhankar Chakraborty at INST. Before depositing LVO by pulse laser deposition, they prepared the substrates of STO. These are titanium oxide terminated STO substrates. And this is the AFM image after growth of LVO-STO. And this is the read patterns. If we count the number of peaks, then we know that 50 monolayer of LVO was grown on STO. And the interface became conducting. This is the resistance versus temperature. This shows that we have a metallic interface at the junction between LVO and STO. Now, LVO is an interesting magnet. In fact, in the 1990s, people studied a lot about this material, and it becomes strongly diamagnetic if it is field cooled across 138 Kelvin. It is so strongly diamagnetic that people thought that they actually discovered 140 Kelvin superconductor at that time. You can see that in this paper, they actually mentioned superconductivity, but of course, transport measurements showed that this is an insulator. And this diamagnetism is not coming from the core Landau diamagnetism of the compound. This is much, much stronger than that. And this is 2 orders of magnitude greater than the diamagnetic susceptibility of polycrystalline bismuths. So what was seen in these experiments is that it has a spontaneous magnetization, and that likes to align in a direction opposite to the applied magnetic field in which it is cooled down across 138 Kelvin. So field cooling across the transition gives a negative resonance for this compound. And I will show you that these negative resonance actually plays out nicely in the interfaces. So as I said, we discovered superconductivity at LVO-STO interfaces, and the superconducting transition temperature is about 250 millikelvin. And the transition temperature goes down systematically as we increase the magnetic field, which is expected for a superconductor. And the superconducting signal disappears above 4.5 kilogauss, which is the critical field that we measure. And this is the HCTC phase diagram as we get it from this RT data. We also observe the critical current of the superconductor. And from the critical current data, one can say that this is actually a very fragile superconductor. Maybe what we have essentially are superconducting puddles. are percolatively connected with each other, because we can see that this zero resistance state is actually seen only at zero field and for very small values of current. So this is the, but features of critical current and the magnetic field dependence of that is clear. So from this, we conclude that this is a superconductor. And these measurements were done at 28 millikelvin. So this is the first set of results that we obtained from the dilution refrigerator that we installed recently. Now, as I mentioned, that LVO is an interesting ferrimagnet. Now, what is it doing in this case? In order to study that in detail, we exposed the system to controlled magnetic fields. What we did, we warmed up the interface to 500 millikelvin, which is the normal state. The superconducting transition temperature is around 250 millikelvin. And what we did, we ramped the magnet from 0 Tesla to +1 Tesla, and then ramped it down to 0 Tesla again. So at zero field, we cooled down the interface, and we found that the superconducting transition temperature has gone down. This is the, I call it the state prepared at 1 Tesla. When I say that, I mean that I have done a 1 Tesla field cycling, 0 Tesla, 1 Tesla, 0 Tesla, and then cooled it down and found that the critical temperature has gone down. If I compare this with the pristine state, then this is what it looks like. This is the pristine state data, and the red line shows the transition after doing the field cycling in the normal state. So in this case, I want to mention that as an experimentalist, one of the suspects is the magnet itself. If by ramping the magnet up to 1 Tesla, if I have a remanence in the magnet, we have done experiments to very carefully rule it out. In fact, we have seen the data that I'm not going to present today unless a question is asked, that we did get dependence of the properties, superconducting properties of the interface. And we found that the remanence field that we measure is also dependent on the gate voltage that we apply. That means the property is of the interface itself. There is no extrinsic origin of that. Now, this is the RT after doing the field treatment. Then we started applied magnetic field in the same direction in which the field cycling was done, that is upward. This arrow indicates the direction in which the field is applied. And we see that with increasing the magnetic field, the critical temperature goes up, and at 0.27 kilogauss, we recovered the pristine state RT back. So from this, we speculate that there is a remanence directed in the opposite direction as with respect to the applied magnetic field, which is there at the interface, and which is a consequence of the field cycling in the normal state. So that means the interface retained the memory of the field cycling at the interface in the form of a negative remanence. And when I apply a magnetic field upward, while the remanence is downward, because this is negative, field cycling was done in the upward direction, the applied magnetic field for measurement first compensates for the negative remanent field that is already present. And we estimate that to be 0.27 kilogauss. And beyond that, when I applied the magnetic field even more, then the RT goes down with goes like this, with the critical temperature going down, as it is expected for a normal superconductor. And the same thing happens for the critical current as well. Up to 0.27 kilogauss, the critical current goes down, and then critical current goes up. Then for the magnetic field beyond that, the critical current goes down systematically as it is expected for a superconductor. So this means the interface actually retained the memory of the field cycling that was done in the normal state. This is the phase diagram, HCTC phase diagram for the magnetic field applied in the same direction as the cycling field, and H max is the maximum field to which cycling was done. In this case, it is 1 Tesla. And we see that the critical temperature goes up, then it goes down systematically. Now what we did, we applied the magnetic field in the other direction. So the maximum cycling field was in the upward direction, but the measurement is being done by applying a field in the downward direction. And in this case, because now this is being added up to the remanence, which is in the negative direction, these two are in the same direction. There is no non-monotonic dependence of the critical temperature on the magnetic field, but with increasing magnetic field, the critical temperature goes down systematically and disappears at 4.5 kilogauss. And same thing happens for the critical current as well. So now, when I plot these things together, we see that depending on the cycling field, if it is along the up direction, then I have a resonance field which is in the down direction. And if the cycling field is in the down direction, then I have a resonance field in the up direction. And this happens at the interface. So from this phase diagram, we can conclude that the idea of the formation of a negative resonance at the interface is valid because the observation is consistent with that. Now, what we did, that means we have been able to successfully write a magnetic state at the interface. We wanted to erase it. For that, we tried different field cyclings, and we found that if we warm it up to 500 millikelvin again, that is the normal state, and do a field cycling with H max is equal to minus 0.5 Tesla. That means if the state is written in the plus direction, upward direction, then I apply a magnetic field of 0.5 Tesla in the downward direction, then the plus 1 Tesla state is erased. So it did erasing of the magnetic information at the interface. I'm not showing too many RT data because that will clutter the slides, and you know what it will look like if I actually show the data. And then we did the field cycling at 500 millikelvin to minus 1 Tesla, and cooled down. We found the resonance pointing upward and erased that by applying a field of 0.5 Tesla upward. And in all these cases, we are going to the normal state to write the magnetic state, and coming back to the superconducting state to use the superconductor as a sensor. So if it is appearing only at the interface, it may be very difficult to measure it by usual magnetometry. But in this case, the superconductor is helping us detect the magnetic state that is written or erased in the normal state. Now, is it something special about 1 Tesla? The answer is no. We can change the H max, that is the field up to which the cycling is done in the normal state. By changing the field up to which the cycling is done, we write different values of resonance. So this is the reading in our case. So for this experiment, what we have done, we have taken this R versus T graph and fixed the temperature here, which is in the middle of this transition. And then we measure the R versus H. It shows a minima, and this minima should ideally come at 0. And because of the presence of the negative resonance, it is shifted in the positive axis. And because the H max, the cycling field was applied in the negative direction, so resonance is in the positive direction. And we see that this minimum, which gives me the resonant magnetic field, is a function of H max, the maximum field up to which the cycling was done. So if you give me a sample by doing some field cycling and not telling me at what field it was cycled, I can do this measurement and tell you from the value of this magnetic field where this dip appears, I can tell you at what field the cycling was done. So that means by doing this kind of experiments, looking at the superconducting properties, we can also read the magnetic information that was written and in the normal state. Now, we can see that superconductivity and magnetism are coexisting and interplaying with each other. So is it possible that this is actually coming from unconventional superconductivity? We first looked at the band structure that our colleague Tanushree Das did at IISER Bangalore. And what he gave us is that in case of LaOSTO, it's only the titanium band that's crossing the Fermi energy. But in case of LVSTO, we have the titanium band as well as the vanadium band, which is crossing the Fermi surface. Now, if both of course, in this case, the strong correlations that are present in LVO are not considered, but if the vanadium electrons are also taking part in superconductivity, then there is a possibility of unconventional superconductivity. In fact, part of this was spoken by my student Mona in another talk, but I will go through the details of that once again. But the difficulty here is that doing spectroscopy, transport spectroscopy like scanning tunneling spectroscopy or point contact spectroscopy on the 2DEG is difficult because the 2DEG is always hidden underneath an insulating layer. So we found a technique to penetrate through this and make a contact at the with the 2DEG by using the ultrasonic wire bonders and perform soft point contact spectroscopy. And at an interface between a normal metal and superconductor, as we know, unreap reflection takes place when the energy of the electron is less than
5 minutes left. Huh?
Okay. How many minutes?
5 minutes.
Oh, okay, thanks. This electron reflects back as a whole when the electron energy is less than the superconducting energy gap. And for charge conservation, a Cooper pair propagates inside the superconductor. And this interface can be modeled as a delta function potential barrier. When the barrier is not transparent, we know that if we measure DI/dV, then these peaks appear at the superconducting, close to the superconducting energy gap. When we have a very large barrier, we have the coherence peaks as we see in STM spectroscopy. But in the metallic regime, when these peaks appear, we know that we are looking at unreap reflection. And these are all for conventional superconductors where the low bias conductance cannot be more than 2 times the high bias conductance. When we did these measurements, we found that the spectra did not look like the conventional unreap reflection spectra. It did have some kind of peak structure here, but at 0 bias, we found a strong peak. In fact, with increasing magnetic field, we found splitting of the peak also, but we are doing more work on that. I do not want to talk about that now. Now, we compared this with some of the calculations done on using unconventional order parameters, where it is possible that the low bias conductance is much larger than the high bias conductance much greater than 2. But we also need to be careful because we know that such things often appear if the point contacts are not made in the ballistic regime of transport. In our case, we found this consistently for all the 6 contacts that we measured on LVO STO. And we recently talked about these aspects of non-ballistic effects in point contact spectroscopy in a PRB paper in 2021, where we also mentioned how we can rule out the contribution of non-ballistic effects. The first one is that the contact diameter should be much smaller than the mean free path, so that we are in the ballistic regime where spectroscopy can be done. The electron does not dissipate energy otherwise. And also for a ballistic point contact, the normal state resistance should not change with temperature, because the normal state resistance will be given by these fundamental constants, the Planck's constant charge of an electron. The bulk resistivity of the materials come into the picture when we have the contact in the thermal regime. And we found that the normal state resistance does not change significantly. And from the normal state resistance, we found the contact diameter, which is much smaller than the mean free path that is known for these 2DEGs. Therefore, we can conclude that probably we are looking at unconventional superconductivity here. I would like to thank our collaborators, Anamika and Shubhankar at INST Mohali, who gave us the beautiful 2DEGs. And then the band structure calculations were done by Partha and Tormoy. And these are the people who did all the measurements, all the data that I presented. And they also installed the dilution refrigerator, that you can see in the background. This is the manipulator with which we transfer samples. And I think that was a bigger achievement than the data, because in absence of the engineers from the company, they installed the dilution refrigerator that we did during the pandemic. I thank DST for supporting the dilution refrigerator. Thank you so much for your attention.
Okay, thank you, Goutam. So talk is open for discussions and questions. Patnaik ji.
Yes, Goutam, thank you again. It's a beautiful talk. I mean, with COVID, without COVID, in spite of COVID, you continue to do exceptional work. So congratulations. My question is, as you know, to establish that the superconductivity is actually coming from the interface. And as you rightly said, the oxygen deficient STO itself is superconducting and around the same TC. And you also mentioned in your talk that there are more evidence that you can do by gating it. You can show that this is actually coming from the 2D. Is there something that you can, these are probably the referee questions that would come. So can you just justify, how do you convince the referee that this is not the substrate STO that is contributing to the superconductivity, but the 2D electron gas that you have at the interface of LVO and STO? That is the...
Okay, so I am not denying that the superconductivity is coming from STO, but the entire STO substrate is not becoming superconductivity. Superconductivity is coming from the STO side of the interface, number one. Number two, it's not that you deposit anything on STO and it will give you the superconducting phase. So far, it has been found that superconducting phase is obtained only for 3 systems, LAO STO, LTO STO, and in our case, it is LVO STO. So, I mean, we do not care about the origin of the superconductivity here. In this case, we are using the superconducting part of the interface as a sensor of the magnetic states that we are writing, reading, and erasing. So it is okay. Even in case of LAO STO, the superconductivity is actually in the STO side, but this is still effectively a 2-dimensional superconductor.
Yeah, that is right. But LAO STO is kind of, there's a lot, you see ferromagnetism and a lot of things can happen. But the key thing is that whether it is happening at the 2D electron gas or that is derived from the substrate. So I think there is a superconductor of LVO KTO also, right? So did you
No,
see
LVO KTO is not superconductor. LVO KTO we are measuring now. So far we did not find superconductivity. EO KTO is superconducting, and the critical temperature is 2 Kelvin.
Now the question is, if the termination is at the titanium oxide, then LVO KTO should also show superconductivity. I mean, why is it all the superconductivity is coming with STO only? I mean, that's I'm not trying to pick holes in the theory, but
yeah, so I was trying to make a similar comment that if it is coming from STO, then why not on all materials deposited on STO we see the superconducting phase, number one, and why the entire STO substrate does not become superconductor? I mean, it may come from delta doped STO, but it is confined at the interface, and we essentially have a 2-dimensional superconductor which is interplaying with magnetism.
Thank you, Goutam. Thank you.
Yeah,
Thank you,
I mean, I'm not denying that it is coming from STO. Yeah. It may come from STO, but it is confined at the interface.
Okay, great. Thank you.
Yeah.
We have time for a quick question. Still 2 minutes. Saurav Srivastava.
Maybe I don't know, but I just want to make a comment here. But suppose if this superconductivity is coming from this STO substrate, then is unconventional QPC di by dB measurement.
Oh, okay. So yeah, let me show this data quickly then. So what we did, this is the data that we did not talk about today. What we did the field, the electric field dependence of the superconducting properties. So this is again the R versus H graph when the temperature is fixed at the middle of the transition, so that we have substantial resistance to measure. And you can see the evolution of this R versus H with applied electric field, and we see that the remanence, that is appearing at the interface, is also a function of electric field. So this means the magnetism and the electrical properties in this case are well connected, and these are the experiments that are still going on. So that is why we think that the both magnetism and superconductivity are appearing at the interface, though LVO is playing a role here, and that is why we think that all the unconventional behavior that we see here may be appearing. Yeah.
Okay, last question, Shroy Datta. Please make it quick. So.
Thank you for the nice talk. Is there any directional measurement like parallel and perpendicular to respect to the magnetic field?
Yeah, so that is what we are doing. We do not have a rotator, and every sample transfer involves huge loss of liquid helium, which we cannot afford. But we are trying to do that. We have just physically rotated the sample, and the measurements are going on. And probably this week we will get some results. Yeah, it is expected, because this is a very thin superconductor. The critical field will be very large, I expect, for the other direction.
Yes, and the last one, just for a quick comment, if you like to make. So this AC versus TC plot that you have, sir, it has a little bit of long tail. Is there any reason for that, rather than a falling sharply at near to TC?
Yeah. So yeah. Let me go to this one. Pointer options. Yeah. So this is what you were talking about, right? So for a conventional, as it is empirically expected for a conventional superconductor, it should have been like this, right? But now it is going like this, and
Yes,
also in
yes,
this case
yes.
it is going like so. Many a times people attribute this to unconventional superconductivity, but we want to be careful because we know that as I said, it is a very fragile superconductor, and most probably it is heavily disordered, and such things can appear from disorder as well.
Thank you so much.
Thank you, Goutam. Thanks for a wonderful talk. And so the next speaker is Tamaghna Hazra from Rutgers University. Tamaghna, do you have your slides ready? Can you just project it? Yeah. Okay, I'll give a warning after 10 minutes that 3 minutes is left. Okay, you may start. Now we go to the last talk of this session, and that is by Mainak Pal from Indian Association of Cultivation of Science. Mainak.
Hello.
Yeah, so I will give you a warning after 10 minutes that 3 minutes is left. Okay, please start.
Okay. So is this visible?
Yes, it is.
Okay. So today I will be talking about vortex unbinding in and out of equilibrium near the Kosterlitz-Thouless phase transition using gradient flow. So this project was initialized by our beloved late Professor Kushan Mujumdar, and currently I am continuing this work with Dr. Arnab Sen. So the key motivation of our work here is to estimate the density of free topological defects in lattice systems. Free topological defects are interesting for a couple of reasons. Firstly, it is the proliferation of free vortices in two-dimensional systems with O2 rotational symmetry, which drives a topological Kosterlitz-Thouless phase transition. Secondly, the mechanism via which these vortices unbind is very well understood by doing RG analysis on the Coulomb gas model. More recently, it has been found that certain aspects of these systems, such as dynamical scaling, depend only on the density of free vortices rather than the full density. For lattice systems, however, estimating the density of free topological defects is not well defined. There have been approaches based on Euclidean distance and a cutoff, and using more sophisticated convolutional and deep neural networks. Our objective will be to provide a simple and natural way to detect the density of free topological defects. For this, we are going to use the Wilson flow or gradient flow used in lattice QCD to get rid of the short wavelength fluctuations in the field configurations. So we are going to apply the gradient flow to the two-dimensional XY model, which is defined on a 2D square lattice, and the degrees of freedoms are planar spins which interact ferromagnetically to all the nearby spins. This model has a couple of peculiar properties. First of all, there is no symmetry breaking transition in this system. It can be shown that even if we initialize the system in an ordered state, even the smallest of fluctuations will drive the system and restore the symmetry. This model supports two kinds of excitations. Firstly, there are spin waves, which are long wavelength modulations of the spin profile of the system. The more non-trivial excitations are topological in nature and are called vortices. These are these configurations have a non-zero circulation around a closed path. For future reference, I have shown here 3 kinds of plaquettes which I am going to use in the future. So as we can see here, we can have a 1x1 plaquette which consists of 4 boundary spins. There can be a 2x2 plaquette which consists of 8 boundary spins, and there is a 3x3 plaquette which consists of 12 boundary spins. So the total circulation will always be an integer multiple of 2 pi. The particular defect shown here is an anti-vortex. So even though there is no order disorder phase transition in the system hosts a topological phase transition, as can be seen by RG studies of the model. This shows that there is a low temperature phase in which there are bound vortex anti-vortex pairs, and in the high temperature phase, these vortices proliferate. We now come to the gradient flow or Wilson flow method. The key idea of the Wilson flow method is very simple. We start with the action of the system and impose a new kind of dynamics into the system, which is based upon the gradient of the action itself. This is used readily in lattice QCD to filter out the short wavelength ultraviolet fluctuations of configurations and result in a smooth and renormalized field. This was first shown by Martin Lucier. We apply the gradient flow to our XY model in a similar spirit. We use the Hamiltonian or the energy functional to derive a very simple flow equation which can be numerically integrated. Our expectation is that under this new flow dynamics, the system will reach a local minima of this H, and as a result, all the short wavelength fluctuations will go away, and hence the bound effects will get annihilated. Intuitively, at low temperature, the gradient flow is a very simple mechanism. As we can see here, the Hamiltonian at low temperatures, apart from some constants, can be written as some grad theta squared term, which results in a heat equation or diffusion equation like flow, which has an averaging radius of square root of 4 tau, tau being the flow time. For high temperatures, however, the exact form of this averaging radius is not known, but there will still be a smoothing effect, and this radius will increase with flow time. We now apply our gradient flow method to spin configurations of the 2D XY model. We start with the spin configuration which is at equilibrium. So the spins are not shown here, but the red dots are the vortices and the blue dots are the anti-vortices. This is generated by some Monte Carlo algorithm. Now, if we gradually introduce gradient flow into the system, as we see, in very short amount of time, all the vortices and the anti-vortices attract each other and get annihilated. We can do the same thing above the critical temperature, and what we find here is that even after a sufficiently long amount of flow time, there are still vortices and anti-vortices present in the systems, which are well separated from each other, and the dynamics has become very slow. So we can say that these residual vortices are free. We can do this gradient flow across all the temperatures in the system, and we find the following. So on the left hand side, we have the bare vortex density, which is at without any gradient flow. This has a few properties. First of all, the 3 kinds of vortex densities of 1x1, 2x2, and 3x3 plaquettes are very different from each other. And also, the vortex density starts to increase even before the critical temperature is reached. We now introduce gradient flow into the system and observe the effects. At very short flow times, we can see that these 3 three different kind of vortex densities are now very close to each other, and some of the vortices which are present below this critical temperature are annihilated. As we increase the flow time further, we see that at very large flow times, all these different vortex densities overlap with each other, and the vortex density only starts to rise after this critical temperature. So this shows us that the vortices which are present below this BKT, which are bound in nature, are annihilated via this gradient flow method at very large flow times. So this demonstrates that in equilibrium, the gradient flow method can distinguish between bound and free topological defects. So following the reference here, we now apply the gradient flow method in out of equilibrium scenarios. We first initialize the system at twice the critical temperature and then linearly ramp it to a zero temperature using different ramp rates. When the system crosses the critical point, it will fall out of equilibrium, and as a result, even in the low temperature phase, there will be many vortices and anti-vortices present. Now, what we do here is that at every intermediate temperature during this ramp, we apply the gradient flow and average over several initial configurations, and we get the following result. This result shows us that the vortex density obtained by gradient flow after this ramp is non-zero even in the low temperature phase. So this demonstrates that the gradient flow can distinguish between free and bound effects even in the non-equilibrium cases. Also, we can see that the smaller the ramp time or the faster the ramp rate, the higher is the number of vortices. As this ramp time is gradually increased, the number of defects decrease. So this shows that the gradient flow is also sensitive to the ramp rate that is used.
Achha, Mainak, 3 minutes left. Okay.
Okay. So to summarize, we have seen that the gradient flow method can distinguish between free and bound topological defects, both in and out of equilibrium scenarios. It will be, we think it could be easier to apply machine learning studies after this gradient flow has taken care of some of the short length wavelength fluctuations. One question we have not answered yet is to how long we should perform this gradient flow. We have used some sufficiently long time, but how long should this flow be exactly depending on the temperature is not known. We think that if we build up an exact relationship between this gradient flow and renormalization group methods, this question could be answered. We wish to apply this gradient flow on other models which support topological defects but host a more conventional phase transition, such as the 3D Heisenberg model. And thank you for your attention.
Okay, thanks, Mainak. We have questions here. So Pratap is the first person. Pratap, go ahead.
That was a very interesting talk. So what I want to know is that I have two questions. One question is that your method of gradient flow, it allows you to access non-equilibrium situation. Is that the advantage over the more conventional RG analysis that one carries out?
No, I think rather it is we can approach these things in lattice systems. The RG method works for the Coulomb gas model, which is in the continuum, but this gradient flow method can be applied to lattice systems.
I see. And the other question is that in this analysis, the fugacity, is it put by hand or it just comes out of the model? The fugacity of the vortex?
I mean, we have not really used any fugacity directly during this analysis here.
Pratap, the short answer is it comes out of the model. So yeah, Mainak is just analyzing the model at the fugacity generated at a particular temperature. So
I see.
Yeah.
I see. No, the reason I was asking is that normally if you have low fugacity, then below the BKT transition, you have some thermally excited just below.
Correct.
So here at long time scales, do you see no vortex, anti-vortex at all?
Below TKBT, this flow actually kills those bound, thermally bound vortex anti-vortex pairs, right? So that's what this method is trying to do. Yeah.
Okay. Thank you.
Okay, any other questions? No. Okay, then again, thanks, Mainak, for your presentation. And that concludes our session, and I'll hand over to Pratap for further announcement or anything. Yeah.
Okay, so we come to the end of the morning session. I think the next session starts at 11:45, if I'm not mistaken. Yes.